Hello everyone, it is time to work on our 7.3 and 7.4 where we will be talking about our equilibrium constant and how to set up the expression and how to plug in and solve for our equilibrium constant value. Alright, so that is 7.3 and 7.4. Okay, so we have the equilibrium equation, which is what is inside this little purple box right here. Be very clear with the vocabulary because this can come back to haunt you if you are not paying attention. Alright, so the equilibrium constant is this capital K. And we learned back in Unit 5 about a rate constant, and I will address the difference in those in just a second and how you notate them. And then we have the equilibrium constant expression. That is this. So, real quick, on the AP exam, typically if you get a free response question that is equilibrium, one of the first things that they ask you to do is write the expression. And when they ask you for that, they specifically mean an expression that looks like this, where the capital letters C and D and A and B are replaced with whatever species they are. It could be, hydrochloric acid or something like that. And then the lowercase letters are some exponent, and we'll talk about that when we get to it. They don't want any numbers in this, with the exception of exponents if they belong there. So I will really hit that home with you guys in just a second. But we learned back in Unit 5 that we had this, rate equals K, concentration of whatever our reactants are, so we'll just have A, it's supposed to be a bracket, and then we have M as our exponent. And this lowercase k was the rate constant. So K stands for constant, but what's really important is that you are not switching them. So back in Unit 5, I told you this had to be a lowercase k. Okay, lovely. Well, in this unit, this has to be a capital K. So very, very, very particular about that, so don't get those mixed up. This particular expression is coming from this equation. And take note that the products are capital C and capital D, and they go into the numerator, and they're raised to the power of their coefficient from the balanced chemical equation, which are lowercase c and lowercase d. And then in my denominator are my reactants, which are capital A and B, and they are raised to the power of their coefficients. So this one is specific for this particular generic equation. But you can also just say that capital K is concentration of your products divided by the concentration of your reactants, and they're all raised to the power of their coefficients. Okay, and that's how you would set up an equilibrium expression. All right, this one is a Kc. You'll notice that there is a lowercase c right here on K. That's probably the most common K that we have. There's actually a lot of Ks. And just be careful. We'll talk a little more about it later, but if they specifically ask you for a Kc, then you write Kc. If they specifically ask you for something called a Kp or a Keq or Ka or Kb, you have to write exactly what they ask you. And when in doubt, if they don't specify what type of K they want, you can just write a capital K. Okay, that's fine, and that's probably the safest bet, because if they just say write the equilibrium expression but then they don't tell you which type to write, then just write K, because that's safe. Because if you write Kc and it's technically a Kp, then you're going to get it wrong. But if you just write K, then you're good to go. However, if the prompt says write the Ka expression, like they actually write this out, then you need to write Ka on your paper. So if you need further clarification on that, just ask me and I will talk to you about it. But C stands for concentration. It is the most popular one. Concentration is moles per liter, and you got to remember which states of matter can be measured in molarity or concentration. And those are going to be things that are aqueous solutions, and these are going to be things that are gases. So gases are the ones that can be measured in pressures and or concentrations. Aqueous solutions are concentrations only. and pure solids and pure liquids are neither. All right, so this is the most common equilibrium expression that you're going to see right here, where you're dealing with basically a concentration. So that's why we have brackets, and I'm going to talk about that because it's so important that you have, number one, brackets if it is a concentration, and number two, that they look like brackets. And you'll see why when we get to something called the KP. And AP is very particular about that. All right, so when we have our gases, when we have the equilibrium constant in the gas phase reactions, it can be expressed in terms of something called a KP. Instead, we'll go back. Sorry. There we go. Where P is because of it's measured in pressures. Okay. So the KP is calculated by taking the ratio of the partial pressures of the products and the reactants raised to their stoichiometric coefficients. So it's still the same. It's still the same thing. Let me clear that. It's still the products over the reactants. The difference is they are in parentheses, or they're in those, not the brackets, and they're raised to the power of their coefficients. We'll have no space. It's still calculated numerically the same way, but how you write it is a little bit different. And don't forget that gases can also be calculated with concentrations, which makes them a Kc versus instead of the Kp. So let's just clarify again real quick. Gases, you can write a Kp expression or a Kc. Now, numerically you calculate them the same way. Products over reactants raised to the power of their coefficients. Aqueous solutions are Kc only. All right. How do you know which one you're doing? You look at what they're giving you. What type of information do you have? If you have moles and liters, that's molarity. That's Kc. Do you have ATMs or millimeters of mercury or torr or something like that? Then you're dealing with a Kp. And so we're going to talk about writing some of those in just a second. Pure solids and pure liquids do not belong in the expression. Okay, they do not belong at all. So they don't have concentrations, they don't experience partial pressures or anything like that, or have anything to do with pressures if you were dealing like gases do. So we omit them from the expression. So here we have the equation, and so this is a good example. So we have acetic acid, which is put in water, it dissociates, and we get the acetate ion and the hydronium ion. Okay, so what happens is it reaches equilibrium. So if I am at equilibrium, then I can write a K expression or an equilibrium expression. For this particular one, they're all AQ, so this one's definitely a Kc. It could not even be a Kp, even if it really wanted to, because they're aqueous solutions. So I'm going to put my products. Here's one. It's AQ. It goes right here. Okay, so that's my acetate ion. Notice its coefficient is a 1, and so its exponent is a 1. I have my hydronium ion, H3O+, is AQ, so it counts, it goes into the expression, and it's right here. These are both products. And then on this side, I have my reactants. So I have the acetic acid, which goes here in my denominator. Its coefficient is 1, so its exponent is 1. And then we have pure water. Notice it's not here. Why? Because it does not go into the equilibrium expression. Only AQ and only gases. That's it. Now, if this was somehow a mixture of AQ and gases, they could go in there because we would still only have just concentrations like molarities for them. But just be aware, no liquids and solids. They will try to trick you on that. All right. Let's take a look. Now, if we are not at equilibrium, or you don't know where you are, the reaction is moving forward, if stuff is happening, you just started, then you're not at equilibrium yet. If you're not sure if you're at equilibrium yet, you're not quite sure if you're there, or if you were at equilibrium but then we disturbed it, because we talked about that in the last video, that we could disturb equilibrium by taking something out or putting something in or changing the pressure. And that type of thing. So that can adjust or knock you out of equilibrium, and then your equation is trying to get itself back into equilibrium. And so when you're not sure, or you know you're not quite at equilibrium yet, you will solve for something called Q. Its name is called the reaction quotient. And it's the same mathematical calculation. It's the products over the reactants. And if we're dealing with concentrations, then they're brackets and they're raised to the power of the coefficients, just like if it's K. It's solved for the same way. It's just called Q because we're not at equilibrium yet, or we don't know if we're at equilibrium yet. All right, so when you're not sure, or if something's been knocked in or out of equilibrium, then we have to take a look at the reaction quotient. So I want to click over here real quick and go up to this one. Okay, so let's just do a quick review of where we are at. Number 1, oh my goodness, it keeps going all the way down to the bottom. Here we are. All right, so number 1, if we want to, we're not sure if we are at equilibrium, or we just started or we disturbed it, then we're going to solve for the reaction quotient. And we can do this at any time during the reaction. Anytime. Even if we're at equilibrium but we don't know it, we can still calculate Q. It's calculated the same way as you calculate K. So if you look down here, products over the reactants, and hold on, let me get rid of this and then do the color code. These are my products and these are my reactants. Okay, and then this is Q or K. And it's C if we have concentrations. So if they're AQ and or gases, they could fall into the QC or the KC. And if they're all gases and we are given some type of pressure, then we are dealing with KPs. And then you can notice the difference in the way that we write them because the KPs have a parentheses instead of a bracket. So be careful of that. That's very, very, very important that you make that notation and the difference between the two. And yes, they are very particular about it. All right, now, if we are calculating or writing the equilibrium constant, then that means we know we are at equilibrium at that point in time, and we still are going to use the same expression. All right, so again, right here, we're talking about KC or QC is if we have some type of molarity, and this can affect aqueous solutions and it can affect gases. Well, that's supposed to be an S, gases. And then we have KP, this is gases only, and then we are given some kind of pressure. Okay, great. So let's look at a couple of these examples that are written here, which are excellent to look at. So let's just take a look. We have this equation. Okay, so for this one, we're going to write a KC expression for sure. Why? Because they're all AQ. So they're all AQ, so I'm going to write a KC. Now, this and this are a product. And these two, copper 2 ion and lead 2 ion, are my reactants. So that means they're going to go in the denominator, whereas copper 1 and lead 4 are my products, so they're going to go in my numerator. So I have the copper 1, which is right here. His coefficient is a 2. That means his exponent is a 2. You see that? And I have lead 4 ion, so I have lead 4. His coefficient is a 1, so his exponent is a 1. Okay. Then I have, get another pen. I have my copper 2 ion right here, and the coefficient is a 2, so the exponent is a 2. And then my lead 2 plus ion, which is right here, goes right there next to him, and his coefficient is 1, so his exponent is 1. This is called writing the equilibrium expression. That's what this is. And if you have gases, and let's say, for example, if you have this equation, they could give you concentrations, which means you have to write one of these, because gases can be either pressure or concentration. So if they give you an equation that's all gases, don't just think it's going to be a KP, because they'll sometimes trick you with that. It could be an equilibrium, it could be a concentration expression, so watch out. Now, assuming that you have pressures of some type. They've given you ATMs, you've somehow indicated that that's what you're working with, then you're just going to go through it step by step by step. So I have my products on the top, which is ammonia gas, and that is right here. And his coefficient is a 2, exponent is a 2. Then we have our nitrogen gas here, coefficient's 1, exponent's 1, and then we also have our hydrogen gas next to him, and his coefficient is a 3 and his exponent is a 3. So this is also Chem expression, okay? And so that's the basics on how you set it up. I want to talk to you for just a second about all of the details of what we're looking at here, because these details will get you and cost you points on the AP exam. Okay, so what are the details? Number one, when I'm writing the KC, it's very important that you have very defined brackets. They don't look anything like a parentheses like over here. They have to be very squared off and defined, and if you think you're going to fake the funk and kind of do something blended in the middle, they're just going to mark it wrong. So that's number one. Number two, when they ask you for the expression, let's say you already have values to plug in, which is what we're going to do in 7.4 in just a second. You already have values to plug in. Well, you cannot just go ahead and plug in the concentrations. So let's say you had concentration of copper and you had concentration of lead and you wanted to go ahead and plug in. Not if they've asked you for the expression. Expression. This is an equilibrium expression. No numbers with the exception of the exponents. Do not put them, or if it's something that has numbers in it like N2, but you're going to list the species from the chemical equation in the expression. Do not put in the numbers that you have. And if you think that's faster, and yes, it is faster, however, if you want the point for writing an expression, then you actually have to write the expression. Right? They're super, 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 super picky about that. Writing the KC is a lot easier for a lot of kids than writing the KP. So I just want to spend a second on that one. All right, KP. So with the KP expression, notice that you use parentheses instead. You use a capital P, P for pressure, it's capital P. And then you have a subscript of who is it. So in this case, my numerator is, there will always be my products, and my product is NH3. So it's the pressure of NH3. His coefficient is a 2, so he is squared. So yes, I know we have this written on the paper, but I just wanted to walk you through it really quickly about how you write it. Open the parentheses. It's very clearly a curvy parentheses. I have a pressure of my reactants, which are capital P, subscript N2, close the parentheses. Coefficient's a 1, so the exponent's a 1. And then times parentheses. Big P, H2, coefficient's a 3, so the exponent's a 3. The other big issue, so number one big issue is not writing the brackets and or parentheses properly. That's one issue. The other issue is that in here, sometimes people want to put a plus sign. Do not do that. This is equilibrium expression. It's multiplication in the math. All right, so in this math that we're going to use to calculate in just a second, there's not a plus sign between them. You put your two products on the top if you have two, like you do here, or if you just have one, that's fine. If you had 3, you'd have 3. As long as they're all either AQ or gases, they go in the expression. But they're multiplied together. Okay, they're not addition. So that's not a big one. I have a few kids every year that kind of want to put a plus sign in there because they see a plus sign in the equation and they just want to stick it in there. No. And your maths will be all wrong, so don't do that. Now, really quick right here in your notes, a few years ago they took this part out of the AP exam. So it's here. Just be aware that basically KP and KC are not necessarily always equal to each other. There is a scenario where they are equal to each other, but that's not important anymore. But they're not one for one. So I could have this equation where I'm given ATMs and molarities. So the expression numerically would look the same, but it wouldn't look the same in terms of the parentheses and the brackets. But numerically, they would calculate similarly, but they would give a different answer. So if I wanted to convert, I would use this equation. Used to be on your formula sheet. It is no longer because you don't do it anymore. So this is not on the AP exam. So it's here if some of you, I know, just are dying to do more because the AP content's just not enough for you. So it's there, but it is not tested on the AP exam anymore. So if you see older problems where they have you convert between KP and KC, those were just prior to this particular rule that came out, I don't know, 5, 6, 7 years ago. I don't even remember, but it's been a ways back since they took that out. All right, so here's our I do for this. So for our I do, we have this equation. So we have this combustion reaction. And so remember, in a combustion reaction, your H2O is a gas, so pay attention. If it were a liquid, it would not be in this equation, so watch out. So it's a Kp. Everybody's a gas, so that means they're going to be giving us some pressures or of some type, ATMs or whichever. And so when I write my expression, I'll just do it over here. Don't just look at it, do it, write it, because you need to actually get that muscle memory going. I have my first product, parentheses, big P, subscript CO2, close the parentheses, 3. Okay, open the parentheses for the H2O. Look at, oops, I'm talking and trying to write something different at the same time. Big P, H2O, close the parentheses, 4, because his coefficient's a 4. Divided by, open parentheses P, and I have C3H8, which is propane, coefficient's 1, exponent's 1, so don't write anything, times, not plus, times, big P, O2, close it, 5. Okay, so that is your expression. So that's how you write equilibrium expressions. So you have some problems to practice writing them. Be careful. Remember, no solids, no liquids. Keep them out of the expressions. So make sure you know how to write them without numbers. I really like that in the notes we separate this out because I have so many kids that just want to jump right into plugging in the numbers. But I'm telling you, on your test, if part A is write the expression, the equilibrium expression, and then part B is calculate the equilibrium constant, you just jump right into and automatically plug the numbers in without actually writing this, you will not get the first point, even though it's all correct. So watch out. So we want to get that point, right? All right, so let's click over. And perfect. Get that off of there. Now, calculating the equilibrium constant. So now we're jumping into 7.4. We know how to write the expression. So we now want to calculate the value of K. So first step, you have your data. Now there's a couple different ways this is going to happen. Number one, they're going to just give it to you. So at 7.4, we're just giving it to you. You don't have to actually figure it out. But some type of lab has been done, you have some concentrations, it's all figured out. Coming up very, very soon after this video, they're not just going to overtly give you the equilibrium concentrations, you're going to have to figure them out, and we'll talk about that. And it's not that hard, so don't make it hard. Then we're going to determine we'll have the concentrations and or partial pressures while we're at equilibrium. Right now they're just going to give it to us in this section. All we have to do is plug them in to the expression, and then we just do our math. So if you don't know how to use your calculator properly, you're going to have problems. This unit will start to get you because lots of times your concentrations are going to be really, really small, and you're dealing with like 1.4 times 10 to the negative 7 times 1.4 times 10 to the negative 3 raised to the power of 2 because its coefficient is 2. And so you have these scientific notation numbers that have exponents, and then there's a numerator and a denominator. And if you don't know how to use your calculator properly, and we've been talking about this, we talked about this year in class. This is the unit that is going to come back and get you. So if you are stuck on that and you need help, please let me know and I will help you, because there's no sense in being able to do all the work and then not be able to actually do it. Okay, so what is this relationship between Q and K? So let's review it real quick. If we're definitely in equilibrium, it's K. If we don't know where we are, and at any point in time, from start to finish to after we disturb equilibrium and screw around with it, back to equilibrium or whatever, we calculate Q. They're the same algebraically. Go back and look right here. They are the same. Okay, we calculate Q and K the same way. It doesn't matter. But what the AP exam likes for you to do, and we're not going to do it yet, but I just want to introduce it so you know, like, why are we talking about Q or K? In 7.4, so in today, we're only calculating K. But again, if you're not sure, you calculate Q, and then you can figure out where you're going. So number one, easy peasy, if Q and K are the same value, then you are at equilibrium. Not a problem. If they're the same, you're at equilibrium, you're already there, nothing has to happen. Because we talked about how if you're not at equilibrium, you will be going in whichever direction you need to go, towards the products or towards the reactants, in order to establish equilibrium. But if you're there, you're there. And so you're just going to stay there. But you have to predict which way is your reaction going to shift in order to achieve equilibrium. Now, every textbook and everything that you are given is going to give it written to you in a way that looks like this, where it's Q and K. And then in this box, you would put some inequality, less than or greater than, or you would put an equal sign. Okay? And then you have to figure out which way it's going to shift in order to help you figure out, is it going to go towards the reactant side or is it going to go to the product side in order to establish equilibrium? Well, it requires you to think, right? Which thinking is great, but sometimes we don't have a lot of time to think on the AP exam. So what I do when it's like this, is I flip it. I write them in alphabetical order. K and then Q. Why? Why do I flip it? And why does it matter? Because when you have two values, like if you know your K value and you know your Q value, you could plug them in. So if K was like, let's just pick easy numbers. We're not going to do like hard numbers. Let's say K was 1.5 and Q is 3.2. You already know, hopefully, which number is greater than or less than, right? So if 1.5 and 3.2, well, 1.5 is less than 3.2. So that means your K value is less than your Q value, right? Which means we go over here. So the reason why I put them in alphabetical order is because when I do it that way, you see the arrow, or the the inequality sign, it points in the direction that your equation will shift. So because it's a less than sign, that means that it's going to shift to the left. It's going to favor the reactants. You're going to form more reactants in order to establish equilibrium. And then if the opposite is true, again, I set up K and I set up Q. And let's say K is 3.2 and Q is 1.5. Well, 3.2 is greater than 1.5. That means K is greater than Q. So if K is greater than Q, look at the arrowhead in the inequality sign. It's going to go to the right. It's going to proceed forward, favoring the products in order to reach equilibrium. So I do switch them around. Even on this one, I would have it automatically switched around. So if I have K and Q and they're both 1.5, they're equal to each other, because when you're going into it, you don't know. And if they're equal, then you're already at equilibrium. But I didn't switch it here because I just wanted you to see that anywhere, textbook, AP exam, they always do it in terms of Q versus K, but I flip it because when you're like on a multiple choice or you're trying to quickly get through the test, because time is going to suck all of your good points away if you aren't being smart with your strategy. This is just a quick strategy to help you very quickly determine which way it's going to shift, and then you can start writing your answer instead of having to pause and think. which way is it going to shift. So just so you know, that's why I do that. All right, now we're not going to compare Q and K in 7.3 or 7.4. We will soon, but it's just a little bit of an introduction of why we have them. This is a review. It's from 7.2, okay? So factors that affect equilibrium. So we can change in concentration. We can add or remove reactants and or products, but if we add a product or remove a product, it can shift the equilibrium. Adding a product or removing a reactant. There we go. If we add a product or remove a reactant, it's going to shift to the left, which the left-hand side is the reactant side. So remember this. If we add a product or if we remove a reactant, then it's going to shift to the left towards the products. Changes in temperature. So we've talked about that. This is all talking Le Chatelier's principles here. Remember that heat is a quantity. Think of it as a reactant or a product. And if you do, then you figure out which way it's going to shift. Same way with the hills or the holes, right? That was in our last video. And then the changes in pressure. So if we increase the pressure, we're going to shift to the side that's going to favor the gases, which is going to higher pressure means we want to go to the side with the lowest number of moles of gas. And if we decrease the pressure, then we're going to go to the side with the highest number of moles of gas. And then remember, AP has a tendency to not talk about pressure anymore. Why? Because everybody was getting those questions right. And so now they talk about volume. And so if you have an increase in volume, that means you have a decrease in pressure and vice versa. Why? Go look at your gas law equations. Okay, that is an inverse proportionality between pressure and volume. One goes up, the other goes down. All right, so that's really important that you kind of have a little grasp on that. Le Chatelier's principle is what the hills and holes, you guys. That's what we learned last time. So you can, if a change of condition is applied to a system at equilibrium, the system is going to shift to alleviate that stress and get itself back into equilibrium. So your equation is under stress if it's not at equilibrium. So it's got to reestablish it. That's its goal. So this principle helps predict how equilibrium will be affected by changes in concentration, temperatures, and or pressures. So we already know how to do that, and you guys, a lot of you already showed me your quizzes in class, so you're mastering it, which is great. Okay, so what are our big takeaways? We have our equilibrium constant, which is capital K, big K. And it's the ratio of the products over the reactants raised to the power of their coefficient, but this only includes A, Q, and G. The reaction quotient, that's Q. You can use that to predict the direction that your equation is going to shift, to the reactants, to the products, or nowhere because it's already at equilibrium. Okay, you use Q anytime in the reaction, you use K when you are at equilibrium. And then we use Le Chatelier's principle to this, okay, these two are quantitative. Numbers. This is a qualitative. So Le Chatelier doesn't use numbers, it just uses if I increase from this to this, or if I decrease this to this, what's going to happen? And so it's not necessarily numerical. You're not going to calculate it, because if you calculate it, you're going to do the K versus Q. But you're just talking about what's happening. All right, so let's go over and do a couple of practice problems. And I've got a few from 7.4. Here we go. And there's some written in your notes, which you guys can work on those yourself. I'm not going to do ones that are already worked out for you. I just want to do a few. I've put 4 screenshots in here. We're not going to do them all. Just do a couple of them, okay? Because once you get this, it's not that bad. All right, so the following equilibrium process has been studied at 230 degrees Celsius. Got it. All right, so we have this equation. Notice that this is a gas, this is a gas, this is a gas. So they're gases. So in one experiment, the concentration of the reacting species at equilibrium are found to be, so they're giving me concentrations at equilibrium. So that means I'm definitely dealing with a K. I'm not dealing with a Q. All right, they give me these values. And it says calculate the equilibrium constant expression. So they specifically asked for the Kc. Now if they just said calculate the equilibrium constant expression and they didn't give me this, then I look at what did they give me in terms of my data, and they gave me something that's molarity, which is Kc, right? So I'm good to go. So they want me to calculate the Kc of the reaction at this temperature. Now they did not ask me to write the expression, but we're going to pretend that they did. So I'm going to write the expression first, because that's the first thing you have to get into the habit of doing, because on the test they're going to ask you for that first. The only time that they wouldn't is if this were a multiple choice question. Okay, so that's my expression. My product is an O2, its coefficient's a 2, so its exponent's a 2. And it's in my numerator. My two reactants are NO and O2. They're gases, so they belong in this expression. And NO has a coefficient of 2, so it has an exponent of 2. There we go. So this is my expression. I'm going to write that before I plug in my values. All right, so now I'm going to plug in and solve. So Kc. All right, so my NO2 is right here. So I have 1 point, oh no, that's not right. 15, try again. All right, I have 15.5 squared. Now notice I can now turn these to parentheses. Why? Because I'm doing a math function. I'm not representing that it is concentration, so they just become parentheses. If you left it as a bracket, it's fine. If you don't know, leave it as a bracket because it's concentration. That makes you feel better because you're not sure. All right, then I have this one. 0.0542, and it is squared, times O2, whoops, this one, 0.127. I'm writing crooked up the page. Okay, so let's do our math. Now, a lot of you have all the proper functions and know how to use like your fraction keys and stuff in here, so that's going to be a little bit faster for you. And some of you don't know how to do it. So I'm just going to calculate out my numerator first. And this is something that you should be working on in class. And if you don't know how to use all of your proper, look, I'm trying to calculate, talk at the same time, all of your proper buttons, then you need to get with someone in class to help you, because, okay, that's what I have for my denominator. Let me just make sure I put in the right number. 0.0542 squared times 0.127. Okay, that's what I got. Because it'll be so much easier if you know how to use your fraction function on your calculator. All right, so now I'm going to divide these two. So I have 240.25 divided by 3.7308 second EE negative 4. And I'm going to try to stop writing sideways on the paper. Kc equals, I get this great big long number. Okay, so let's take a look at our sig figs. I have my yellow highlighter back. Thank you. I have 3 sig figs, 3 sig figs, and 3 sig figs. My concentrations, which I'm using to plug in to here. So this is not part of what I'm calculating, so it doesn't count. 3 sig figs, 3 sig figs, 3 sig figs. I'm calculating with 3, 3, 3, so my answer shall have 3. My calculator says 643,963.7611. So I need 3. 1, 2, 3. All right, as always, you look back one space, and so you could easily just write this 644,000. Okay, that's fine. You could do that. You could also put it in scientific notation. Most of the time on the AP exam, they're going to put this little dude in scientific notation. If you forgot, 1, 2, 3, 4, 5, and the 5th. Now, here's something that I didn't mention earlier. K values do not have units because they can have all kinds of different types of units. So equilibrium constant K does not have units. Rate constant K has units, and those are very significant, right? We had to figure out how to do those and get all our points from the rate constant K, but equilibrium constant K does not have units. It can vary depending on what the expression is, so it's a unitless number. And so this is my answer, and I'm going to put it in a box. Yay or nay? Process that. Okay, I have a few more. There's one. I'm going to do that. I'm going to do 3 because it's a pressure. I will do this one. All right, so at 250 degrees Celsius, phosphorus pentachloride decomposes to form phosphorus trichloride and molecular chlorine. Expect them to make you write that equation as well. So here's our equation. If the equilibrium partial pressures of PCl5 and PCl3 and Cl2 are 0.875 atm, 0.463, and this respectively, that means that the first species listed is the first number, the second species listed is the second number, and the third species is the third number. Okay, that's what that means. What are the equilibrium constants? What is the equilibrium constant Kp at this temperature? Again, temperature has got nothing to do with the sig figs that we're dealing with. It's just telling me that these go together. All right, first thing first, we got to write our expression. It's a Kp. They told us it's a Kp, so I'm writing Kp. If they didn't tell me, I could just write K, and it would be fine. All right, let's practice it. Open the parentheses. Big P. My first one is a PCl3. Close the parentheses. This equation's balanced. Do a quick check that it's balanced. So its exponent, exponent is a 1. Open the parentheses, big P, Cl2. Exponent's also a 1. Divided by the reactants, which is big P, PCl5, close parentheses. Expression. Now, let's plug in and do the math. Okay, so my PCl5, they gave me first, and that's this one. It goes in my denominator. Let's color code them to help us see it. PCl3 and Cl2. Okay, so my PCl5 is 0.875. Again, it's a unitless number, so don't worry with those. PCl3 is 0.463. and Cl2 is 1.98, and that's my Kp. All right, so we'll do this one. This one's a little bit easier to deal with because all of our coefficients are 1, which means our exponents are also 1. And let me pay attention to my calculator because some of my buttons are not the best. Okay, so my Kp is, calculator says 1.0477 and on and on and on. So I need 3 sig figs. So I have 1.05 is my Kp. 3 sig figs. All right, that's it. Now I will tell you that number 4, which I have here. So here's number 2. Let's pause on that for a second. If you want to pause it and practice it, do it. And then number 4. You can pause it and practice it. With this one, they give you, let's see, calculate the pressure of O2 if NO2 is this and NO2 is that. Equilibrium constant for this reaction. Oh, here it is. I was like, where's those data missing? No, it's not. This is the Kp. All right, so the Kp is this number, 158. And so they gave you the NO2 and they gave you the NO, and they want you to solve for this. So in this expression here, let's just write the expression. Let's just do it. We have Kp equals P of NO squared, P of O2 to the 1 divided by P of NO2 squared. So they have given you this value, they have given you this value, and this one. And so you have to solve for this. It's just algebra. Plug in and solve. All right, so that's 7.3 and 7.4. If you were in my class, you can do that one. If you want to verify with me your answer when you're done, that's fine. I will help you with that. Otherwise, have a great day. Bye.